Hi everyone, today's video is going to focus on an application of the work we've been doing with finding extreme values of functions. And we call these problems optimization problems. And really all these problems boil down to is modeling a scenario with an equation and then trying to either find a maximum or minimum value for that equation. So we're going to outline a basic strategy first and then go through a few examples to show you how these problems work. So in terms of strategy, the first thing we're going to need to do is to develop one or sometimes two equations to model our situation, and we're going to decide which one we're trying to optimize. And again, when we say that, we mean something that we want to either maximize or minimize depending on the scenario. That's what we mean by optimizing it. Okay, if we needed two equations, we're going to substitute the equations so that ultimately we only have one variable, so one equation and one variable. And then we're going to find either the maximum or the minimum. And again, this is what we've been doing this whole chapter, right? We do that by taking the derivative of our function, setting it equal to 0, and then solving to find those critical values. Now the last thing we need to do is to make sure we answer all parts of the equation, and I'll talk to that as we get into an example. So let's look at one. This first one that we do, and I think actually the first two that we do, are only going to require us to write one equation to model our scenario. So here's the scenario. It says the apartment rental company has 1,600 units available, of which 800 are currently rented at $300 per month. A survey indicates that each $5 increase in monthly rent will result in 20 new leases. And so our question is, how much rent should be charged to maximize revenue? So we're trying to find a maximum value that's going to maximize our revenue. So we know a few things. We know that our revenue is going to be equal to the number of rented apartments times the actual amount of the rent. So if we multiply the apartments we have rented by the rent, that's our revenue. Now, our unknown, our variable here, it's talking about this $5 decrease in monthly rent. So our question is, well, how many times should we decrease it so that we can maximize revenue? So I'm going to set my variable here. My variable is going to be the number of times the rent is reduced. All right, so let's look at our setup here. I'm going to call my function r, and it's going to depend on x. So we know our base number of rented apartments is going to be 800, and our base rent is going to be $300. And so now our question is how to incorporate this x. Well, we know that each time we decrease the rent, we're decreasing at $5. So I'm going to look at my amount, and we're saying each decrease is going to be decreasing at $5. Now, each time we reduce the rent, we're adding 20 new leases, so 20 new rentals. So here, to our number of rented apartments, we're going to add 20x. So that's how we're going to generate our equation. Now, I know I'm going to have to take a derivative, so to make this a little simpler to work with, I actually want to expand this out. So we can do that really quick here. So we've got, let's see, this is going to be 240,000. And then we've got plus, let's see, what's that going to be 6,000 x minus 4,000 x. And then I'm going to get minus 100 x squared. So if I simplify that a little bit more, I've got 240,000 plus 2,000x and then minus 100x squared. So there's my equation that models my situation. And again, I have one equation, just one unknown, so we're all set. So now that we've got our equation, we're going to take the derivative. r prime of x. So my 240,000 drops out. I have 2,000. And then the derivative of my negative 100x squared is going to give me minus 200x. And now that I've got the derivative, I'm going to set it equal to 0 and solve for x. So I'm going to get 200x equals 2,000. And when I solve, I get x is equal to 10. Now, here we have to be careful. So this kind of speaks to number 4 here. What we know right now so far is we have x equals 10. Remember, that was the number of times the rent is decreased. That's what we've found out so far. But if I look for what my problem was actually asking for, they didn't ask me that. They want to know how much rent should be charged. So now we've got to go ahead and plug this back into our expression for the rent to actually answer the question. So the rent is going to be 300 minus 5, and we know we're reducing that 10 times, so we get rent is at $250 to maximize our revenue. All right, let's look at the next problem. Now, this one says an example that requires 2 equations. That's not actually true for number 2. We'll see that in number 3. Number 2 is very similar to the one that we did in class. So we have an open top box that's made by cutting congruent squares of side length x from the corners of a 54 by 30 centimeter sheet of paper and bending up the sides. So the first question is, how large should the squares be to make the box hold as much as possible, right? So make the box hold as much as possible. That tells us we're looking for a maximum. And then they want to know what is the resulting maximum volume. So we've got 2 questions, and again, we got to make sure we answer all of those questions. So for my setup, I've got my piece of paper, and I'm cutting squares out of the corner, and those squares have length x. So now I know if this was 54, the remaining length is going to be 54 minus 2x because I cut off those 2 corners. And then here for my width is 30 minus 2x, again because I cut off those corners. Now for volume, I know that's going to be my length times width times height. So I'm going to have 54 minus 2x times 30 minus 2x. And then my height of that box when I fold up the edges is going to give me a height of x. Excuse me, sorry about that. Now, one thing that's actually going to be important here that I need to consider is actually my limitations on x itself. So remember, x is the size of the box that I cut out. It's going to be folded up to make the height of my open top box. So I know x has to be greater than or equal to, or excuse me, greater than 0. If it's 0, I don't have a box. So it has to be greater than 0. Now, looking here, I also know x has to be less than 15 because of this constraint here. If x is greater than 15, then I get a negative dimension here, which can't be possible. So in the end, I'm looking for the value that's in between those 2 numbers. So here to expand this out, I'm going to go ahead and use my calculator to help me do that. So I'm going to do 54 times 30. I'm going to get 1,620. And then I've got minus 60x minus, for right now I'm ignoring this x, I'm just dealing with my parentheses here. Let's see, minus 108x, and then I've got plus 4x squared, and I still have to multiply that all by x. I'm going to write this in descending order here. So I've got 4x cubed. This is negative 168x, so when I multiplied it, I got minus 168x squared, and then I've got plus 1,620x. So part 1 is done. I've modeled this situation with an equation. It's in one variable, so we're good to go. So now I'm going to find the derivative. which is easy enough. This is a nice polynomial to work with. So 12x squared minus, let's see, 336x, and then plus 1,620, and then we're going to set that equal to 0. Now, this problem ends up actually not factoring well, and because of the numbers, this would be an appropriate time to use a calculator. I'm going to do this. What we could do is we could use quadratic formula, and we could use that to find the value of x. But I actually want to use my calculator because I want to connect this to the work we were doing just in the last section with extreme values. So here's what I know. I have my derivative, and I'm going to graph it. I know that if I'm looking for a maximum, that's going to be where my derivative, in this case v prime, if it's a max, I'm looking for where v prime changes from positive to negative. So instead of going through the work of using the quadratic formula, since I'm using my calculator anyway, here's what I'm going to do. I'm going to go to y equals and plug in my equation. So 12x squared minus 336x plus 1,620. And again, I'm looking for a 0. Now, I'm going to go to my window, and I'm going to set my x between 0 and 15. It looks like I already did that. Let's see. So now if I go to graph it, I can see in between 0 and 15, I cross the x-axis once. You can see my derivative was positive and it changed to negative. So it makes sense that there's a max there. So now I'm just going to use my calc menu to find that 0. So I'm going to trace up to where it's positive here. I'm going to go until my y value turns negative, hit enter, and if I hit enter again, it's giving me a 0. Wait, something doesn't look right here. I know that's actually not the value. Oops, okay, I found my mistake. The process is fine, I had the wrong equation. So it's 12x squared minus 336x plus 1,620. If you were paying better attention than me, hopefully you caught that. Again, process is the same. I can still see I've graphed the derivative. It changes from positive to negative at this 0, so I'm going to use my calculator to help me find that 0. So here we've got a positive value. Y has changed to negative, so I hit enter again, and I get x is approximately 6 point, if I round that, 6.190. Now, we could have used quadratic formula and we would have gotten the same thing. So my first question said, how large should the squares be? Well, our squares should be then 6.190 by 6.190 centimeters. That would be the size of the squares. Now, the resulting maximum volume means I'm just going to take this value and plug it into our formula for volume. So V of 6.190 is going to be approximately, we can just put this into our calculator. Let's see, I've got 54 minus 2 times 6.190 times 30 minus 2 times 190. And then x is 6.190, and we get 4,539.402. So 4,539.402. Since it's volume, I have cubic units, so centimeters cubed. Again, so a nice way of using the calculator to check your answer there, or to actually find your answer there. All right, last problem. Now this is actually where we're going to require two equations. So let's see why that happens. So it says a rancher wants to construct a rectangular corral using 200 feet of fencing, and he decides to build it adjacent to a barn. So what's happening is we have a barn wall, and off of that barn he's going to build the corral. So what dimension should the rancher use to construct the corral so that it will enclose the largest possible area? So what I want to do is maximize the area. So the equation, if I'm trying to find the area of this rectangular corral here, I know that's going to be my length times width. So I'm going to call this x and y. So my area is equal to x times y. Now the trouble I have here is that I have two different variables, x and y, and I need it just one. So this is where my second equation is going to come in. I know if this is y, this dimension is also y. And I'm going to use the fact that I have 200 feet of fencing. So that tells me that x plus 2y has to be equal to 200 because that represents the amount of fencing I'm using. So now I can solve, and I know x equals 200 minus 2y. So now I can go ahead and substitute that back in, so I just get this in terms of one variable. So now I'm going to have my area in terms of y is 200 minus 2y times y, or negative 2y squared plus 200y. So now I have an equation in one variable, and now the rest of the process is going to be the same. I have a prime of y. We're going to take the derivative. Excuse me. Let's see, we've got negative 4y plus 200, and we're going to set that equal to 0. This gives us a nice equation to work with. 4y equals 200, which means y is 50. Now, we haven't answered the whole question. So what I know right now is this width, but I need my other dimension here. So I need to solve for x. X we said was 200 minus 2 times y. Well, y is 50, so x is equal to 100. So I know my dimensions of the corral are going to be 50 feet by 100 feet. Now, obviously, you could have called this y and these two x. It doesn't matter as long as your final dimensions, you do the correct calculations to get that answer. All right, so that is optimization. When we're back in class, you'll have a day just to work with these problems and make sure everything makes sense. All right, thanks. See you back in class.